Welcome, everyone. It is my great pleasure to welcome today's speaker, Professor Alessandro Morbidelli from the Observatoire of Cote d'Azur. His achievements are so diverse that it is hard to introduce him without taking it too long. Let me try. His research interests include celestial mechanics, small body dynamics, extrasolar planets, and planetary dynamics. He has received numerous prestigious awards, such as the CNRS Silver Medal from the National Center for Scientific Research, Janssen Prize from the Astronomical Society of France, Margier Bourdet Grand Prix of the French Academy of Science, and the Urey Prize from the Division of Planetary Sciences of the American Astronomical Society. He has been elected associate member of the Royal Academy of Belgium and the French Academy of Sciences. He has served as editor of Icarus for a very long time. He has written more than 250 papers, more than 50 invited review papers, and a book. And an asteroid is named after him. He is an avid skier and an amazing role model to young scientists. So for the audience, I request you to type your questions in the chat box and we will take them as appropriate. And let me, on behalf of everyone, let me thank Morbi for agreeing to give this talk. Morbi, I give the stage to you.
Thank you very much, Surav. Thanks for the invitation. It's a pleasure to speak to you. You know, this pandemic is horrible, but the good side of it is that with these seminars online, one can actually communicate much further away than one would usually do, because, you know, traveling across the world just for a day of seminar is typically not what was done. So today I would like to speak about planet formation and evolution. But given the diverse audience of physicists and astrophysicists, I would like to discuss some key processes that help us understand the diversity of planetary systems. What is this diversity about? So to discuss the diversity, let's first review briefly the structure of the solar system. The solar system is clearly structured because we have 8 planets, which are divided in 2 groups. The inner group is the group of the terrestrial planets. These are relatively small planets. The Earth is the biggest, and these planets are rocky, and they are, well, at the distances of the order of the Earth-Sun distance of 150 million kilometers. Further away, we have a group of 4 different planets, which are called the giant planets, starting from Jupiter to Neptune. And these planets are called giants because they are, right? Jupiter weighs 300 times the Earth mass, and Uranus 15 times, and the other planets in between. But not only these planets are bigger, they are also made differently. Whereas the terrestrial planets are rocky, the giant planets are contain a lot of gas. Jupiter and Saturn are mostly gaseous planets. For instance, for Jupiter, the 300 Earth masses total, at least 260 are hydrogen and helium. For Uranus and Neptune, hydrogen and helium amount for a few Earth masses out of the total of 15, 17. But still a lot of hydrogen and helium, the same gases that make the sun, which are basically completely absent among the terrestrial planets. All the planets of the solar system, both terrestrial and giants, orbit the sun on orbits which are basically circular and almost coplanar. And it was thought in the past that every planetary system should have looked like ours, basically because it's a general belief that the laws of physics are universal. And so if you have the same laws everywhere, they should produce the same results everywhere. And all the models developed for the formation of the solar system in the past were developed with the underlying idea that this model had to work in 100% of the cases, producing all the time the same result. The discovery of the extrasolar planets came as a shock. Already the first planet discovered by Major and Kelose in 1995 was a Jupiter mass planet that, instead of being at a distance from the star comparable to the sun, Jupiter's distance was much closer to its star than Mercury is from the sun. And today we know many more extrasolar planets. This is a plot not particularly up to date, but the situation didn't change so much, showing as black dots the extrasolar planets that we know, and in red, in comparison, the planets of our solar system in a diagram that reports on the horizontal axis the distance from the central star in astronomical units. So the Earth is a distance of 1 astronomical unit from the sun by definition. And on the vertical axis, it's the planet mass in Earth masses. As you can see, the collection of extrasolar planets that we see falls mostly in 3 groups. There is the group of hot Jupiters that you see here. These are Jupiter mass planets, more or less, but so much closer to the central star that they are heavily irradiated by the star. So the atmosphere is really very hot, hence the name hot Jupiters. Then we have another group of giant planets that we call warm Jupiters, because still they are Jupiter mass or a few times higher, and they are much further from the star, nevertheless, typically closer to the star than Jupiter. As you can see, most of these giant planets are at 1, 2 AU, so fill the place that in our solar system is occupied by the Earth and Mars. Some planets are as distant as Jupiter, but the number of planets seems to decline with distance. And indeed, if you go very far from the sun, there are some planets we can detect by direct imaging, but these planets are actually very rare. So somehow the number of planets has to decay with distance from the star, even if we don't know exactly how it decays. There is a gap, as you can see, between these 2 groups. It's not totally empty, but is only scarcely filled. And this gap is real. It's not due to observational bias. And then there is the 3rd group of extrasolar planets that is called the super Earths. These planets are called super Earths because they are bigger than the Earth and typically up to masses comparable to Uranus and Neptune. So sometimes they are also called mini Neptunes or mini Uranus. You can see also some planets which are smaller than the Earth, but these planets orbit stars which are smaller than the sun. So in terms of planet-star ratio, these are also super Earth planets. And okay, so as you can see, most of the giant planets that we observe fall in the region of a parameter space where the sun, the solar system has no analogs, right? We don't have hot Jupiters here, we don't have warm Jupiters, we don't have super Earths. Our planets fall in a region of space which is empty, but this is due to an observational bias, most likely, because our planets are too small and too far from the star to be observed elsewhere with our current techniques. And the only planet that we can observe around another star with our techniques is actually Jupiter. Jupiter is the only solar system planet observable elsewhere with other techniques. The strange characters of extrasolar planets is not just in their distance from the star and masses, but also the shape of the orbit is quite weird, particularly for extrasolar giant planets. So our planets, as I said at the beginning, have basically a circular orbit, and the shape of the orbit is parameterized by a parameter called the eccentricity. If the eccentricity is 0, the orbit is a circle, like this black one. But if the eccentricity is larger, the orbit becomes more and more elliptical. And this is an example of an orbit of 0.6 and another orbit with an eccentricity of 0.9. And this red triangle shows the eccentricity, these semi-major axis properties of the orbits of the extrasolar giant planets. So as you can see, the giant planets are typically either hot or warm, so closer to the sun than Jupiter, but their eccentricities are not low like those of our planets in the solar system. They can be very large, even up to unity. And in the solar system, only comets have such a large eccentricities. And indeed, for fun, if you take the orbit of the comet 67P, the target of the Rosetta mission from the European Space Agency, this was its orbit, say a major axis of 3 AU and an eccentricity of 0.6. So what we are discovering around other stars are giant planets on cometary orbit, essentially, which is quite amazing. The hot Jupiters only have a preference to have very low eccentricity, but this is because of tidal damping that damps the eccentricity of the planets really quickly. And actually, the absence of planets above this giant curve that you may or may not see, it's a little bit pale, I'm sorry. This this region is void because tides become so strong that an eccentric planet up here would immediately become a circular planet down here. So this is for giant planets. Giant planets are really very eccentric, and super Earths is sort of different. So whereas giant planets often are eccentric and alone in their system, super Earths often come in systems which look like mini solar systems, mini terrestrial planet systems, and their orbits are more coplanar and more circular. This is, for instance, an example, just to give one, of a Kepler-62 system compared to the terrestrial planet system in our solar system. So the diagram is in scale in terms of orbits and in terms of physical sizes of the planets. So if you can see, this system, which contains 5 planets, has orbits that are all inside the orbit of Venus, and 3 out of the 5 planets have very close orbits to the central star, well smaller than the orbit of Mercury, and the planets are all but one a bit bigger than the Earth. So that's why they are called super Earths. So despite the observational biases prevent the discovery of a solar system like ours, as I said, Jupiter would be the only planet that we can discover elsewhere. The observations already tell us that 70% of the stars have planets that don't exist in our solar system. So this 70% of the stars have planetary system different from ours because we don't have the kind of planets that they have. And only 1% of solar type stars seems to have a Jupiter on an orbit like Jupiter, so quite far from the star and quite circular. So this means that our solar system is not typical, and that's why I said that the discovery of extrasolar planets came as a shock, because we thought that our solar system would have been essentially generic in the mathematical sense of the term. So the modern research in planetary science basically now tries to understand the origin of the diversity of planetary systems, why planetary systems can be so different from each other, and why our solar system is so atypical. And the holy grail would be even to predict which fraction of planetary systems are similar to the solar system, and so which can host an Earth like ours, maybe inhabited like ours. And of course, this is a holy grail. We are not there at all. And what I will try to discuss today is some ideas to start to understand the origin of the diversity of planetary systems. So let me review the few steps that we think are common to all stars in order to form planetary systems around them. So when a star is forming, it is surrounded by a disk, a protoplanetary disk of gas and dust. And this is a general property, and it's due to angular momentum conservation during the collapse of material towards the central star. And indeed, when we observe just young stars, they're all surrounded in disks. So the disk is a general property of stellar formation, disk of gas and dust. The dust is initially very small, micron size, even less, but the dust starts to coagulate and stick to each other due to electrostatic forces and grow. And as dust grows, 2 things happen. The dust sediments on the midplane of the disk and also starts to have a radial migration towards the central star. How much dust, how big dust can grow just by sticking through electrostatic forces? This has been the object of a series of laboratory experiments, many of which led in Germany, who's a real leader in the field. And it's found that as long as at the beginning, the monomers, the small dust particles, stick through these electrostatic forces and form fractal aggregates, and these aggregates can then collide with each other and merge and reduce their fractal dimension. But once they start to grow big enough, the collisional energy becomes too large, and then this aggregate starts to lose pieces and then even catastrophically disrupt. So it seems that for silicate monomers, it's difficult to grow aggregates beyond a millimeter in size. Maybe in the ice, if the ice is not too cold, it's close to the sublimation temperature, so to 150 Kelvin, the sticking properties are better, and maybe the aggregates can reach some centimeters or even decimeter in size. But then when the ice becomes very cold again, it's difficult to stick, and then we are back to something of the order of a millimeter in size. Now, the question is this a limitation of the experiments or our understanding, or is this real? I would claim this is real, because when you take a meteorite is a piece of a planetesimal, a piece of an asteroid that comes to Earth and we can analyze. We can break it open and see what are the basic constituents of the meteorite. This is an ordinary chondrite, and you see that the meteorite is a collection of grains, most of which are called chondrules, some of which are called calcium aluminum inclusions. And you see that these chondrules have more or less a characteristic size. Well, it can be different by a factor of a few, but we don't see a huge size distribution. And the typical size is, yeah, of the order of a millimeter. It's very rare to have something bigger than a millimeter. So this millimeter limit in the growth of the grains that we see in laboratory experiments is probably real, because we see in meteorites that the basic constituents are very rarely bigger than a millimeter in size. So when we build our theories to start to produce something macroscopic like a planetesimal or a planet, I think we need to start with grains that are at most millimeter in size. If we take grains much bigger, we cheat a little bit. Maybe we can take centimeter grains when there is a lot of ice, but when there is no ice, we should limit ourselves to a millimeter. So how can we go from multiple grains of a millimeter in size to something bigger? And the breakthrough idea in the last decade or so has been, or maybe even 15 years, given that I'm now quoting a paper from 2006, is that these particles that sometimes I will call grains, sometimes I will call pebbles, but it's synonymous, through interaction with the gas, tend to clump, to form clumps. And there are two mechanisms, for instance, discussed in the literature, that can form clumps of dust. One is during the sedimentation of the dust on the midplane through an instability called the Kelvin-Helmholtz instability. The other one is clumping during radial drift due to an instability called the streaming instability. I decided to give an illustration of the first one, but actually the two are analog. So this is a movie taken from this paper, and this shows the density of dust in this diagram, where the vertical axis is the distance from the midplane, 0, the middle of the figure is the midplane, and the horizontal axis is the azimuthal direction around the sun. The colors denote the density of dust. As the dust concentrates, the colors will go from dark blue to bright yellow. So if we run the movie, first we see that the dust tends to sediment around the midplane and forms a thin layer. But then an instability kicks in. It's the Kelvin-Helmholtz instability, creates turbulence. So the dust cannot remain confined on the midplane, forming high density layers on the midplane. It's dispersed over a given thickness. But because of turbulence, you see that dust is now not forming a broad uniform band. The dust is concentrated in these turbulent structures. So locally, in height and azimuth, you can have dense clumps of dust. And sometimes these clumps become so dense that the self-gravity of the clump can hold all these particles together and have them contract to form a compact planetesimals. And the modern simulations of this kind of instability shows that the planetesimals that are formed are typically 100 kilometers in size, with some spectrum in the size. It can be as low as 10 kilometers maybe, and grow up to a few hundred kilometers, maybe even 1,000 kilometers, although this is not so sure. And so we call these objects planetesimals. You have to think them like asteroids if they are not icy, or Kuiper belt objects, or comets if they are icy. And indeed, when we look at the size distribution of asteroids or the size distribution of objects beyond Neptune in the Kuiper belt, we see a preference for 100-kilometer objects. Most of the mass is actually carried by 100-kilometer objects if you exclude the very few very big objects. Okay, then from these planetesimals, we have to try to form the planets. And there, two ideas are on the ground. The first is that planetesimals, of course, once they are formed and they are numerous enough, can collide with each other. And now the planetesimals being sizable, they have some gravity. So when they collide with each other, the gravity can hold the two colliding objects together, producing something bigger. This is a way to produce protoplanets. at least at the beginning, when we start with these 100-kilometer planetesimals. And this process has been studied for many, many years. This is a process of oligarchic growth, of runaway growth, oligarchic growth, extensively studied in Japan by Kokubo and Ida, but also many other groups worldwide. An alternative idea has been proposed also in the last decade, is pebble accretion. It says that the biggest of these planetesimals, once they reach a size comparable to the size of the moon, well, they're still embedded in the disk of gas and dust. And so they can keep accreting the dust from the gas and can grow by accreting this dust. This process is called pebble accretion. Pebble accretion kicks in once the body starts to be sizable, as I said, the mass of the moon, and then can become indeed the dominant process. So it can become a process that allows growth to be faster than just by planetesimal collisions, and this because of two reasons. If a planet grows just by accreting planetesimals around it, because planetesimals are fixed in the disk, they don't migrate in the disk, they're too heavy for gas drag to move them around. Once the planet accretes the planetesimals in its neighborhood, well, it's in an empty region, so it stops accreting. So the growth of a planet by accretion of planetesimals tends to stall relatively early. This dust instead drifts through the disk because it undergoes gas drag. And so even if a planet accretes all the dust in its neighborhood, the neighborhood will be replenished by the drift of dust. So there is the planet can become isolated from the dust, but at much larger masses. The second advantage of the dust is that the accretion cross-section is much bigger than for a planetesimal. This is an animation showing a planetesimal that tries to grow by accreting other objects. And these two objects come in this animation with the same impact parameter, as you can see, and the same initial relative speed. But one of these two objects, the black one, is another planetesimal. So it's not very much affected by gas drag. So in this close encounter, the orbit of the incoming planetesimal is deflected, but the impact parameter was too big and there is no collision. The planetesimal is deflected and goes away. But the red object is the dust particle for which gas drag is very strong. And you see that despite the impact parameter and the initial velocity is the same, once the orbit starts to be bented, gas drag increases enormously and the dust particle spirals down and lands onto the accreting body. So the accretion cross-section is clearly much bigger for dust than for other planetesimals. And these two facts, the lack of isolation and the cross-section, which is bigger, make pebble accretion really a very efficient process that probably dominates the growth of a planet once it starts exceeding the mass of the moon or the mass of Mars. Now, the question is, okay, so the pebble accretion may explain the growth of the cores of the giant planets, because I think the giant planets form in two stages. First, a core, a solid core formed of about several Earth masses, maybe 10 or 20, and then these cores accreted gas around them and became giant planets. But the solar system has this structure that I was showing at the beginning. We have only small planets inside and big planets outside. Can we explain this dichotomy? Can we explain why the big planets only formed in the outer disk, whereas only small planets formed in the inner disk? And I would say the Earth even took a long time to form. Probably by the time the gas disappeared from the protoplanetary disk, the terrestrial planets' precursors were all of the mass of Mars, whereas Jupiter was already fully formed with a core of 10 Earth masses. So the huge contrast in terms of masses of the protoplanets produced in the inner disk versus the outer disk. So we have proposed a possible explanation for the origin of this dichotomy, and this is based on the size of the dust, the size of the pebbles, which is related once again to the sticking properties I was discussing before. So in the protoplanetary disk, there is a gradient of temperature. The gas is very hot close to the star, relatively cold away from the star. So there is at some location a transition that we call the snow line, beyond which water can be solid in form of ice, and within which only refractory material like silicates can be solid, and water is in the form of vapor. As I said before, silicate grains have poor sticking properties. So it's unlikely that silicate grains can be bigger than a millimeter, but ice is more sticky. So we can imagine that beyond the snow line, the dust, the pebbles, can build centimeter-like objects, which are sort of dirty snowballs with millimeter-sized silicate grains entrained in an icy matrix. These icy snowballs drift towards the sun, and when they pass through the snow line, the temperature becomes too large for the survival of the ice, so the ice sublimates away, so we lose half of the solid mass. Not only, but the silicate grains are released. And so in the inner disk, we have half of the solid mass, but we have grains to accrete, which are much smaller than the original grains beyond the snow line. And pebble accretion is very sensitive on the size of the grains. So for instance, if you take two objects initially of the same mass, say half a moon mass, one inward of the snow line, the green one, and one outward of the snow line, the red one, because this one can accrete from bigger pebbles and this one only from millimeter-sized silicate grains, the growth rate is very different. And this is what comes out of a simulation. The body beyond the snow line grows much faster and can reach 20 Earth masses by the time that the inner body, despite starting with the same mass, just because it accretes, has half of the solid mass at its disposal and much smaller grains, accretes much more slowly and reaches only a mass of Mars or so. So we think this can really explain the dichotomy of the solar system, why big stuff, solid stuff formed beyond the snow line and only small planetary embryos formed in the inner disk. I stopped my simulation here at 20 Earth masses because when a planet reaches about 20 Earth masses, then the planet starts to isolate itself from the dust flux as well. Why is that? Because at 20 Earth masses or higher, depending on disk viscosity, the planet starts to open a shallow gap in the disk. So what this plot here on the left shows is the result of a hydrodynamical simulation. The sun is down here. The vertical axis is the distance from the sun. This is the azimuthal angle around the orbit. And the planet is here at 1 in these normalized units. And the colors denote the density of the gas. So you see that on the orbit of the planet, there is a deficit of gas. That's why the color is dark blue. But elsewhere, there is more gas, bright green. And the planet launches a spiral density wave, as you can see. And as you can see, there is a sort of overdensity of gas in this region. Then look at this plot on the right. The vertical axis is the same. And the horizontal axis now tells us what is the rotational velocity of the gas, the orbital velocity of the gas normalized to the Keplerian velocity. And so, as you can see, far away from the planet, close to the star, or very far from the star, the gas rotates around the star at a speed which is somewhat sub-Keplerian, lower than Keplerian. And this is why the dust feels a headwind, a drag, and migrates towards the star. Near the planet, the gas motion is very messy because of the perturbation of the planet. But here, in this overdensity of gas, you can see that consistently, the rotational speed of the gas becomes larger than the Keplerian speed. So the gas is no more sub-Keplerian, becomes super-Keplerian. And this super-Keplerian speed is more and more pronounced as the planet is bigger and bigger. The blue curve is for a 20 Earth mass planet, the red for a 30 Earth mass planet, the pink for a 50 Earth mass planet. Now take a dust grain in the outer disk. Because the disk in the outer disk is rotating in a sub-Keplerian motion, the dust particle feels a headwind, feels a drag, and it wants to migrate towards the star. But this migration eventually has to stop where the disk turns from sub-Keplerian to super-Keplerian, because then all of a sudden the particle doesn't feel a headwind anymore, it feels a tailwind. So it's accelerated by the gas instead of being dragged, slowed down by the gas. So the dust is stopped here, it doesn't reach the planet, so the planet has to stop growing. And also all the other planets which may be growing inwards of the orbit of this planet now starve because the flow of dust from the outer disk to the inner disk is completely shut off. And Jupiter, growing in the disk, eventually exceeded all this mass threshold, 20, 30, 50 Earth masses, because eventually reached 300 Earth masses. So this undoubtedly happened in the solar system. And we think that this is the key to understand the separation of distinct reservoirs in the solar system, both in terms of chemistry and in terms of isotopes. And indeed, there is a clear segregation between the properties of planetesimals formed in the inner disk and planetesimals formed in the outer disk. So we call this the Jupiter barrier. And this diagram shows you an artist's view of the Jupiter barrier. Basically, there is a giant planet growing, and the dust accumulates outside of the orbit of the giant planet. The inner part of the disk still has a lot of gas, but very little dust, because this continuous resupply of dust from the outer disk into the inner disk is shut off. And this is an artist's view, but corresponds more or less to what we see. Sometimes when we observe disks around young stars, we observe transition disks. And transition disks are disks that have a lot of dust outside and the cavity of dust inside. There is still gas in the cavity, but very little dust. And we think that this is due to the formation of giant planet at the border of the cavity. So going back to this diversity issue, up to now, everything I described is quite general. So all stars forming should have the same happening around it. So in a general way, we expect that around each star, there is a disk, that only in the outer part of the disk, water is solid in the form of ice. And so only in the outer part of the disk, big planets can form of multiple Earth masses. Whereas in the inner part, because of these grains are so small, we can only form small planetary embryos, maybe the size of Mars or not even. This should be a generic start of any planetary systems. So where is the diversity coming from? There is another generic law of physics that should apply, is that once planets become big enough, they interact gravitationally with the gas in the disk. And as a result of this gravitational interaction, they tend to migrate. And migration is proportional to the mass of the planet. So migration is important for planets when they reach an Earth mass or more, whereas it's negligible as long as you have only small planetary embryos of a Mars mass or less. So generically, what happens is that after the planets grow big beyond the snow line, they should migrate inwards, whereas the other small embryos more or less stay there. And this, of course, creates a lot of mess, because you have one planet that's moving around, entering the realm of all the other smaller planets. And this, of course, provides instability, scattering, and scrambles the order that up to that point a forming disk should have had. And we believe that migration is probably the key to understand the diversity of planetary systems, because messing up this original order opens up to the possibility of developing a diversity of final outcomes. This is typical of mathematical chaos. When you have chaos, chaotic dynamics, small changes in the environment, in the parameters, in the initial conditions, in the environmental conditions, can lead to very different outcomes in the end. So to illustrate my point, but without any pretensions to be exhaustive here, I will show you 3 cases that can form some planetary systems that we see. Okay, so let's first all based on migration. So let's recap a little bit. So we think that big planets of the order of a few Earth masses form initially only beyond the snow line. Inside the snow line, the planets are very small, so small that I didn't even put them in this simulation. Here I put down a dozen of protoplanets. The masses are illustrated by the colors here. So these are initially all a couple of Earth masses, 3 Earth masses. We are still in the gas disk, so you can imagine we are looking at the system from the side. The star is here. And as I said, planets, once they become Earth masses or more, migrate towards the star. So these planets forming beyond the snow line migrate inwards, because migration is size dependent. During the migration, not all the planets move at the same rate. They can collide. building bigger planets. And at the end, migration brings everything close to the star, and migration stops only at the inner disk edge. There is more and more evidence that the disks are not extended all the way to the surface of the star, but disks are truncated by the magnetic field of the star. There is what is called the magnetic cavity, where the dynamics of the gas is totally different. So basically, the density of gas is very, very low. So what we get here, you can see, is a system of typical of super Earths, where our planets have a few Earth masses, maybe up to 10, 12 Earth masses, what we call the mini Neptunes, and they cluster very close to the star at the location that we think corresponds to the original disk edge. And indeed, this kind of configuration is observed around half of the stars, more or less. Half of the stars have this kind of super Earth systems at about 0.1 AU of distance. But the solar system does not belong to this category, and many other stars don't belong to this category. So what else could happen? So a possibility is that among these protoplanets that formed relatively big beyond the snow line, the innermost one, so the closest to the snow line, grew a little bit bigger for some reason, and big enough to start to capture gas from the protoplanetary disk, so to become a giant planet like Jupiter. Jupiter has a core of 10, 20 Earth masses, and is 300 Earth mass total made of gas. A giant planet also migrates towards the star, but more slowly. So let's see what happens. We have that the planet migrates towards the star. The other cores would like to migrate much faster, like the previous simulation, but they have Jupiter on the way. And it's not easy to bypass Jupiter, to run to the inner edge of the disk. Jupiter is big, tends to block planets in resonance behind it. And so these planets tend to cluster behind Jupiter. There is not much space, so there are several mutual collisions so that these planets can grow. But at the end, they stay behind Jupiter. Only rarely, in about 10% of the simulation, one of them can bypass Jupiter and run into the inner edge of the disk. In most cases, they all stay behind Jupiter. Giant planet migration rate is such that typically at the end of the gas disk phase, they end up in the warm Jupiter region, 1 to AU. So in this case, we have a typical warm Jupiter. We have no close-in super Earths because the candidate super Earths have remained beyond the giant planet. So it starts to look like the solar system in the sense that we don't have the close-in super Earths. But of course, Jupiter is the position of Mars. So this is not really the solar system as we know it. So what could have happened in the solar system? Well, in the solar system, in all evidence, not only the innermost body beyond the snow line grew to become a giant planet, which we call Jupiter, the second one also created a lot of gas to become Saturn. And Jupiter and Saturn together have a gravitational game that we understand, but it's a little bit more technical, so I can describe that in the questions if you like. But this gravitational interaction prevents the planets from migrating towards the sun. If anything, they tend to migrate outwards. Okay, so let's assume they don't migrate at all. And this is what's happening. So Jupiter and Saturn stay in place, and the planets behind them now have not just Jupiter to bypass, 2 giant planets to bypass is basically impossible. So they cluster in resonance behind the giant planets. Some have been ejected. They tend to form a system. The system is metastable, as we will see in a moment. At some point, it becomes unstable. And by becoming unstable, by mutual collisions, will produce 2 planets of the masses of Uranus and Neptune. Here we go, of about 15, 17 Earth masses. So in this case, we have no close-in super Earths. We have Jupiter and Saturn. We have Uranus and Neptune forming beyond. And the region of the terrestrial planets has remained virgin. Nobody has disturbed this region. So my small protoplanets, the Mars mass protoplanets built from silicate grains, can do their own dynamics on long time scale and build the terrestrial planets, because this becomes a protected region thanks to this barrier that Jupiter and Saturn offered, and preventing the migration of Uranus and Neptune and its precursors. Incidentally, we think this is a very good model for the formation of Uranus and Neptune. Uranus and Neptune have a peculiarity that their spin axis is very inclined or with respect to the orbital plane. And if these planets have grown only by pebble accretion, the spin axis should have been perfectly vertical, and it's not. Also, Saturn has an inclined spin axis, but this is due to some spin orbit resonance that we understand. This is not the case for Uranus and Neptune. So the only explanation given for Uranus and Neptune is that these planets suffer the phase of giant impacts. And the way building these planets in this model is from giant impacts, because we started from protoplanets of 3-5 Earth masses, and these protoplanets clustered behind Jupiter and Saturn. And because there was not enough space, they collided until forming these larger planets. So these planets did form by giant impacts, and then their spin axis orientation is random. So if anything of this is true or partially true or nearly true, we would expect a correlation, you understand? So we would expect that when we see close-in super Earths, close to the star, there is no giant planet further away. And when there is a giant planet further away, if it formed from the protoplanets closest to the snow line, it should have retained all the other planets behind its orbit. The giant planets might have migrated down to the warmer Jupiter region, but the inner region should be empty. So of course the solar system would belong to this category. Now, do we see this correlation or not? This is open to debate. Some papers say yes. Barbat et al. Focused on the systems with a known warm Jupiter and looked for super Earths and found none. Other papers like Bryan et al. Did the opposite. They looked for systems with super Earths, and they looked in the radial velocity measurements for trends suggesting the existence of giant planets further away, and they claim that many have this kind of trends. So the jury is still out to discuss. Whatever will be the result will be interesting. If we find that there are many super Earths, even when there is a cold Jupiter, a warm Jupiter, it probably means that this giant planet does not grow from the innermost embryo, the closest to the snow line, but further away or sufficiently late in order not to block the pebble flux and give the time to super Earth to form in the inner system. We really don't know. What happens after the disappearance of the protoplanetary disk? Because up to now, everything I described is still in this disk of gas and dust. Well, we think that after the gas disappears, there is something very general that affects most planetary systems, is that the planetary systems become unstable. As long as gas is in the system, its gas damps. So it retains the system stable. It protects it from too strong perturbations. But once the gas goes away, the planets are not damped anymore, and they can become unstable much more easily. We think we find evidence in the collection of extrasolar planets for instabilities taking place in almost all systems. If you take the super Earths, for instance, in this motion of migration that I showed before, where super Earths formed farther from the sun, migrate to the inner disk edge. At the end, the super Earths are very closely packed, and they are all in resonance with each other, which means that the ratio between adjacent planets, the ratio of periods of adjacent planets is the ratio of integer numbers. So typically we get a distribution like this. This is the cumulative distribution of the planets that we get at the end of migration in terms of period ratio for planets nearby. So as you can see, it's a staircase, and each step of the staircase happens when the period ratio is the ratio of integer number, 3 to 2, 4 to 3, 5 to 4, 7 to 6. This means that the systems are very compact. They are in resonance. What we observe is this gray distribution. This is the cumulative observed distribution of period ratios between adjacent planets. Totally different, nothing to see with what we get through migration. But after the gas disappears, most of these resonant planets are so closely packed, so numerous, so in resonance, that it's a very delicate system that tends to become unstable very quickly. And once they become unstable, their final distribution is this one. We have here two curves, red and blue. It's two different experiments, but basically it's statistically undistinguishable and very close to the distribution that we see. So from that, we conclude that indeed, most of the super Earth systems, even after they migrate and cluster at the inner edge of the disk in resonance, after gas dispersal, they become unstable. And that's why we see this kind of distribution and not this kind of distribution. Only few systems remain unstable, and we do see them. The TRAPPIST system is one example. There is another example, Kepler something, people by Millis, I don't remember the number, I'm sorry, which is in resonance. There is a few % of planetary systems that preserved the initial resonance configuration, but 95% of the systems at least must have become unstable to explain their period ratio distribution. This is for super Earths. For giant planets, we have another indicator, which is this eccentricity. And how to get these eccentricities? Because the planets are born typically in the disks on circular orbit. And an idea developed from Ford and Razio, studied by many people. Surav Chatterjee made a seminal paper with Ford on this, other people as well. Sorry, Surav, I will show a simulation from Sean Raymond because he gave it to me. I'm sure you observe the same. So this is a system as we envision it with the sun, the disk. This time the disk formed 3 giant planets, okay, and many smaller planets or planetesimals. Once the disk of gas disappears, if we run the simulation, for a while the giant planets can stay stable, and then you can see that the smaller planets can try to build terrestrial planets, but at some time the giant planets become unstable, and this leads to mutual scattering, mutual encounter events. And the result is that the system of giant planets has exploded. One planet has been ejected in interstellar space. One planet has been sent a little bit closer to the sun and has acquired an eccentricity of order of 0.3 to 0.4. One planet has been ejected to sent to 25 AU, also with a large eccentricity of order of 0.4, 0.5. If you do many of these experiments and you do statistics, as Surav and Ford showed, and Jurek and Tremaine and so on, and Nesvorny and Bourget, you find that giant planet instabilities really reproduce the observed eccentricity distribution of giant planets that we observe. So which make people think that when giant planets form, they don't form often, they form only in 10–20% of the cases, but when they form, probably multiple giant planets form, and when the gas goes away, these planets become unstable. And by the way, by becoming unstable and eccentric, as you can see and you have seen before, these terrestrial planets that were trying to form closer to the star have all disappeared, because if a giant planets become eccentric, all the terrestrial planets become eccentric and they can collide with the central star. Now, we think that our solar system was not an exception in that sense. We think that also our giant planet system became unstable at some point. The reason is that in the simulation I showed before, those with Jupiter and Saturn not migrating and helping the formation of Uranus and Neptune, I don't know if you paid attention, but at the end, the giant planet system, Jupiter, Saturn, Uranus, and Neptune, was also extremely compact, was stretching only from 5 to 12 AU, and the planets were all in resonance with each other. So this orbital configuration that we get when we build the giant planets in the disk of gas is very different from the orbital configuration that we have now, which is this one, with Jupiter and Saturn further away, Saturn 9 AU, Uranus and Neptune much further away at 20–30 AU, no resonances between the planets, a little bit of eccentricities. So two things, either, well, our model for the formation of the giant planets and migration disk is wrong, or we need to find a process that after the dispersal of the gas disk is able to change the orbit of the giant planets and turn the initial configuration into the current configuration. Well, we think that this process exists and it's an instability. And this is the core of what is called typically the NIS model. So the NIS model, there are many versions starting from 2005, but the most modern version starts with the giant planets as they come out of migration simulations in the disk of gas, the same simulations that produced Uranus and Neptune I showed before. And what we do now, so the initial conditions of the giant planets are given. They're not arbitrary initial conditions. And we remove the disk of gas, and the only assumption is that beyond the original position of Neptune, there was a disk of planetesimals, the ancestor of the current Kuiper belt, stretching from the position of Neptune up to about 30 AU, and containing in total a total mass of about 20 to 30 Earth masses. And what we see is the following, is that as this times evolves, the times is here, there are interactions between the planets and the planetesimals. The planetesimals become more eccentric, and because they have encounters with the planets also shake because of the encounters with the planetesimals. And after some time, which can be short or long, depending on the initial separation between the inner edge of the disk and Neptune, the system becomes unstable. And when the system becomes unstable, the giant planets have encounters with each other, the giant planet system spreads, Uranus and Neptune are sent into the planetesimal disk, disperse the planetesimal disk completely, and by doing so, their orbits recircularize. And at the end, we end up with Jupiter and Saturn partially eccentric, Uranus and Neptune more circular, and the radial distances of the planets, which are essentially the same that we have today. So this initial migration through an instability is consistent with the current structure of the solar system as we observe it today. Now you will say, but we are confused. You said before that if there is an instability of giant planets, the giant planets become very eccentric. You said at the beginning, our planets are almost circular, and indeed your planets here have eccentricity of not even 0.1. So what happened? Well, in the simulations that we do, we find many kinds of outcome, but we can essentially class them in two groups. There are the simulations where by chance, in this instability, Jupiter and Saturn encounter Uranus and Neptune, but by chance they don't encounter with each other. And these simulations are the good ones, like the one I showed you before, are those that reproduce the solar system with Jupiter that remains on a quasi-circular orbit, Saturn, Uranus, and Neptune on their good orbital positions. But in many other simulations, despite we start from the same initial conditions, just by the law of chaos, during the instability, Jupiter and Saturn have mutual close encounters. And then it's the same process as I showed before that Saurav studied. So giant planet scattering, this destroys the giant planet system. Uranus and Neptune are ejected. Often Saturn is also ejected from the system. Jupiter typically acquires an eccentricity of 0.4. And an eccentricity that is actually comparable with the eccentricities of the warm Jupiters that we observe. And each red dot is a warm Jupiter observed by radial velocity technique, and its size is proportional to the radius, to the square cubic root of the mass compared to Jupiter. In order to have the diagram in scale, this is the distance from the star, and this is the eccentricity. So to conclude, I would say that we start to understand the diversity of planetary systems, without, of course, having to say that the laws of physics are not universal, which would be crazy. The laws of physics are universal, and the basic processes ruling planet formation and evolution are also universal and the same everywhere. There is planetary growth, mostly by pebble accretion for major planets, planet migration due to gravitational interaction with the disk, orbital instabilities, particularly once the system is not dissipative anymore because gas has been removed. But migration in particular introduces a lot of variability because it introduces chaos. And chaos is very sensitive to initial conditions and environmental parameters. And so a huge variability of final outcomes can occur. And I just showed a few in order to be brief. So if we want to reproduce the solar system, which I remind you is atypical, okay, only 1% of the solar stars have a giant planet like Jupiter or with an orbit like Jupiter, distant and circular. Well, if you want to reproduce the solar system in this narrative, we need to invoke that at least 3 events, lucky events, happen. The first one is that of all the planets that were growing beyond the snow line efficiently because the pebbles were relatively big, the innermost one became big enough to start to accrete gas and become a giant planet, so forming Jupiter. And it's because Jupiter was the innermost big planet that it prevented all other planets to migrate closer to the star, crossing the terrestrial planet region. But Jupiter alone would have migrated to 1 AU, more or less. And so the second lucky event is that behind Jupiter, the second planet also grew quickly enough and massive enough to also start accrete gas, become a giant planet, and become Saturn. And Saturn has the right mass to block Jupiter migration or even reverse it. I didn't speak about the reversal of migration. It's also a possibility. And this is why Jupiter did not become a warm Jupiter, but stayed out there and left the terrestrial planet region untouched, allowing terrestrial planets to be able to form. And finally, the last lucky event is that after the disappearance of the gas, when our giant planets became unstable, like all good systems of giant planets, by chance, Jupiter and Saturn did not encounter with each other. If they had done that, Jupiter would have become very eccentric, and anything trying to form in the inner terrestrial system, in the inner solar system, in the terrestrial planet region, would have become extremely eccentric as well, and therefore would not have the terrestrial planet that we know today. So we are not yet able to quantify the likelihood of each of these events, but you can understand that each of these events is not too probable. And of course, if you have to combine those, it's a product of probability. So we're not able to really put a number on any of this, but this gives a sense that the solar system has to be rare, and indeed is observed to be rare. But of course, as I said, if anything goes wrong, the terrestrial planets may not form. They may be wiped away during the migration of super Earths, wiped away during the migration of giant planets in the warm Jupiter region, wiped away when giant planets become eccentric. So we need to live in a system that allows the formation of habitable terrestrial planet, however improbable that is. So there is no doubt that even if the solar system is a minority among the planetary systems, maybe it's no chance. It's not by chance that we live in such a system. So I end here, and I'm happy to take your questions. Thank you very much.
Thank you, Morbi, for the excellent talk. I will clap on behalf of everyone. If you have questions, please raise hands.
Yes, there is one.
Okay, can you unmute and ask the question? There was one and then I lost her.
Saura, I have a question. I can't raise my hand because I'm a co-host. So,
okay, go ahead.
Yeah. So, Alessandro, I just want to ask you. So, do all giant planets migrate? I'm asking you this question because, of course, you're aware of this so-called directly imaged planets, which are at several tens and several hundreds of AU from the host star, and they are also much more massive than Jupiter. You know.
Yes. Yes.
So how do they? I mean, it's clear that they probably don't migrate, and they are. You know?
I agree. Okay, so in principle, all planets migrate because they perturb the disk, and by action-reaction principle, they suffer forces from the disk. They make them migrate. But the migration speed depends on two things. Depends on the viscosity of the disk, and depends on the mass ratio between the planet and the local disk. If the disk has a very low viscosity, the gas has problem in rearranging itself. And so the push on the planet is reduced. Type 2 migration, which is the migration of giant planets, is in principle proportional to the disk viscosity. So in the past, it was thought that viscous disks are relatively viscous. Now new models of disks tend to argue that the disks have lower viscosity than was thought. And indeed, observation of dust sedimentation from ALMA seem to suggest small values of this alpha viscosity parameter. So giant planet migration may be slow, but I would say never inexistent. But for these planets imaged by direct imaging, they are also very big. Typically, they are multiple Jupiter masses, even 10 Jupiter masses.
Yes.
In an outer disk, which is not too massive in the end. And there, the inertia of the planet matters. The disk A light disk cannot move a heavy planet. It's unphysical. So the type 2 migration proportional to viscosity is only valid in the limit where the disk is much, much more massive than the planet. When you have a planet forming massive compared to the disk, maybe by gravitational instability of the gas or so forth, or the then of course the inertia of the planet matters. So that would add the third aspect, is that these planets that we see by direct imaging, some of them at least, are not individual. They are in groups, like the HR 8799 system or PDS 70. And these planets are in resonance with each other. In the HR 8799, I'm not sure the number is correct. It's the giant planet system with 4 giant planets seen in direct imaging since 2009. The planets are in 2-to-1 resonance, and in the PDS 70 system, the planets are in the 3-to-2 resonance. And these are the configurations, like the Jupiter-Saturn configurations, that prevent migration, slow down migration a lot. And may not be by chance that they are in this kind of configuration. In the PDS 70 system, which is observed in the disk, this is actually what we describe, what we invoke for Jupiter and Saturn. Even the mass ratio between PDS 70b and PDS 70c is a little bit like Jupiter and Saturn. And simulations done by people by taking these planets in the disk, a group of Baruto and Zhu, show that the planets are moving out, for instance. And so if you have multiple giant planets in resonance, the planets don't migrate inwards anymore, and they can even migrate outwards.
A related question is, the disk lifetimes are also not very long. I mean, disks live only for a few million years, and so the Jupiter-like planets to form, it takes about a few million years. I mean, it's
absolutely.
So for the disk, for the migration to happen, this has to be sufficiently massive. So there is this, it's a very fine tuning is required. I mean.
So yeah, if you form a planet at the end, of course, there is not much time to migrate. If you form a planet by core accretion, there is the first phase, which is the type 1 migration, which is very dangerous. It's fast. So when the core is a few Earth masses, it tends to migrate very fast. And so when you start to form a core, you better start to accrete the gas quite rapidly, because otherwise you tend to lose your planet. It tends to become a super Earth in a edge of the disk. These distant giant planets probably formed by giant gas gravitational instability. So they formed as giant from the beginning. They had no type 1 migration phase, and that helped preserving them. And then possibly the disks are photoevaporated by FUVs, so they find themselves in a disk that is not very massive for very long.
Thanks.
Morbi, I have a question. So this is related to the 2 different qualitative architectures of planetary systems that you described. So one is the super Earths that are in close orbits, and there are no Jupiters or giants outside.
Yes.
And the other is the opposite, right?
Yes.
So I was wondering, could you also not have these, the short orbital period super Earth sequence created by pebble drift-like things that happen early, and then at a later time you form, just by chance, you form a giant?
Yes, absolutely. It could. So if observations show that this scheme is not correct, and you actually do find, like Brian claims, that there are super Earths and then behind the giant planet, yeah, you need to form the inner super Earths before the giant planet comes and block the flux. Because when a giant planet comes in, it blocks the flux. I think there are no doubts about it. So everything has to happen before. Yeah. Or you can imagine in a scheme like this, that this guy becoming a giant planet is not the innermost one, is the fourth. And then you have the free ones enjoy free ride and become super Earths. And the giant planet is the fourth one and migrates slowly and retains the others behind. but the first 3 have become close-in super Earths. That could also be a possibility. This scheme is expected only if my assumptions are true. That is that you have fast formation of the most massive planet at the snow line.
Okay. Thanks. Ambrish? Ambrish, please unmute yourself and ask.
Yes, am I audible?
Yes.
Yeah. Hello, sir. My question is about period ratio resonances. So,
Yes.
so it is a two-part question. What's special about two planets if they are in a period ratio resonance, and what effect does this resonance have on the planetary orbits? Does it tend to stabilize the orbits, or does it tend to destabilize the
Sure.
orbits?
Okay. So when planets migrate and approach each other, say, for instance, the first planet has reached the edge of the disk, so it cannot migrate any further. The disk is stopped. The second planet is still migrating. It's approaching the planet. So the period ratio decreases, right? Because the inner planet is fixed, there's a fixed period. The other planet is migrating inwards, so its period is decreasing. So P2 over P1 decreases. And by decreasing, it crosses these integer ratios from time to time. Every time it crosses an integer ratio, there is some resonant interaction between the planet. This is due because the relative configuration of the planets becomes periodic. For instance, if you are in the 2-to-1 resonance, every 2 orbits of the inner planet, the outer planet makes 1 orbit, and then the configuration repeats. So the perturbations sum up in some sense. This is why in a resonance, something special happens. And what we see is that depending on the migration, and these resonances become stronger and stronger as the planets are closer to each other. So what we see is that depending on the migration rate, the planet can cross the first resonances because they are too weak, but then eventually goes in a resonance that is strong enough, and the resonant perturbations block the incoming planet and capture it in resonance. And at that point, the planet has to stay in resonance. The period ratio doesn't change anymore. The action of the disk, you say the disk is still pushing. Where is this force going? This force is going into the deformation of the orbit. Up to that point, the migrating orbit was circular. After it's captured in resonance, it becomes more eccentric. But the disk is also damping the eccentricity. And so at some point, you reach an equilibrium eccentricity, which is the result of the equilibrium between the excitation of the eccentricity due to the migration prevented by the resonance and the direct eccentricity damping from the disk. So this capturing resonance is well understood. It happens every time there is convergent migration. It happens in the solar system even now. Now there is no gas, no planet migration. But if you look at dust, the dust of the comets, the dust is migrating towards the sun because of the Poynting-Robertson track. And it clusters in resonance with the planets. And we do see resonant rings of dust. Okay. So it's really a real phenomenon. And so resonances are stabilizing agents in general if there are only few objects in resonance. So 2 planets close by tend to be unstable, but if the 2 planets close by are in resonance, they can be stable forever. This is the case, for instance, of Pluto relative to Neptune. Pluto is even crossing the orbit of Neptune, but it's stable because it's in the 3-to-2 resonance with Neptune. If you move Pluto away just outside of the resonance, it would become unstable in a few 100,000 years and would be rapidly ejected from the solar system. But if you form resonant chains, so you don't have just 2 planets in resonance, you will have 3, 4, 5, 6 planets in resonance, like the TRAPPIST system. It becomes a mess because each planet is resonance with the neighbor, with a different frequency, with a different period ratio. And that becomes a really very fine-tuned system and very fragile system. It's enough that there are some little external perturbations scattering through some remnant planetesimals. This is also another idea of Surav. Tides moving one planet relative to the other. But even sometimes the planets all by themselves, because there are so many resonant frequencies involved, that they become unstable. So what we see is that chains of 2 planets in resonance, 3 planets in resonance are very stable. But chains with many planets typically become unstable. So like the extrasolar giant planet eccentricity suggests that when giant planets form, at least 3 giant planets form. This period ratio distribution of super Earths suggests that when super Earth forms, half a dozen of them forms, because if only a few formed, they would remain stable, they would remain in resonance. So planet formation, when it happens, it's efficient, produces many planets, and because the system is overcrowded, that leads to instability.
Is there a very simple physical way to understand, like you explained that when a planet is moving inwards towards the sun, towards the star, when it, let's say, reaches a 3:2 resonance, you said that the resonance keeps it from moving inward. So how does that happen? Is there a way to understand that physically or not?
Not so easily during a conference like this. Maybe on a board and writing a few sketches, one could give some sense. There are, of course, papers formalizing all of it. And if you look, for instance, at a paper by Picchieri and myself in celestial mechanics, is my last paper in celestial mechanics. Okay. We try to explain the capture of 2 planets in resonance. There are great papers by Batigin and I have a problem of memory. Also explaining that. So the literature is full of a mathematical explanation. It's something very well understood. You have to start to write down a few equations, a few Hamiltonian, and it comes out. If you want to have just a physical sense, basically at a resonance, the resonant planet behaves like an oscillator. So it wants to oscillate around the resonant location. Okay. So migration is pushing the planet in, but the resonance, as soon as the planet passes inward of the resonance, pushes the planet out. And then it depends on how strong is this restoring torque. If the resonance is weak, the inward migration wins, and so the planet goes away. But if the resonance is strong enough, as soon as the planet passes the resonance, the restoring torque is strong enough, is stronger than the migration force, and actually the planet flips back and comes outside of the resonance. Then, of course, it tends to go in again, but then the resonance pushes it out again. And so the planet oscillates in this manner. And because there is this continuous migration force, this goes into the deformation of the orbit, and the orbit becomes eccentric.
Thanks.
Okay, you're welcome.
Vikas?
Yes, I am audible.
Yes.
So, like, as you know, sir, there are a lot of parameters which affect the planet formation, right? So, but how the elemental composition of a disk will affect the planet formation?
Yes, of course. So, but all disks more or less should have the same composition in terms of, they have a gradient of temperature, and then you have refractory elements inside, volatile elements condensed outside, and so on. So everything I discussed in some sense general. Of course, this can be more or less warm, more or less cold. So the location of this no line can be closer in, further out. It also depends on time, because temperature of the disks evolves with time. A parameter that seems to play a role is the so-called metallicity. So the metallicity is the ratio between hydrogen and helium and all the other elements. Actually, the opposite of this, the inverse. All the other elements over hydrogen and helium. If you have a high metallicity, that means you are in a corner of the galaxy that has been polluted by supernova and so on. Then, of course, you have much more elements that can become solid compared to the gas. And then it's easier to build planets, of course. You have more material at your disposal. And indeed, there are a number of correlations which are observed with the metallicity. Stars which are more metallic are more likely to have giant planets. Stars that are less metallic are more unlikely to have giant planets. We also see correlations for super Earths, right? And because we see that the masses of all stars tend to have super Earths independent of metallicity, but the masses of the super Earths do depend, have a correlation with metallicity. Again, if you have more material, you can form bigger stuff and bigger planets. So the metallicity certainly plays a role. Metallicity certainly plays a role.
Thank you.
Jan?
Hello,
Yes.
am I audible? Thank you for this talk. So when you were talking about disk migration, you told that super Earths, for the migration of super Earths, the speed is proportional to the mass. The more massive planets can migrate much faster. But when a giant planet is formed, it was migrating much slower.
Yes.
Why is that?
Okay, you heard right, and you noticed the sort of inconsistency there. So congratulations, very good. Indeed, there is a big change in regime when a planet starts to be massive enough to open a gap. So now where is my figure? Okay, here. So until a planet is not too massive, so the planet does not change the surface density distribution in the disk. You only generate a spiral density wave, but no gap. In that case, we call type 1 migration. And type 1 migration is indeed linearly, the migration speed is indeed linearly proportional to the planet mass. But once the planet becomes big enough, and big enough depends on the viscosity of the disk, it starts to open a gap in the disk, like you see here. You see that along the orbit of the planet, the gas is partially depleted. It's not greenish anymore. It has become dark blue. Then the migration process changes. In particular, once the gap becomes deep, the planet is locked inside the gap. And in order to migrate, the entire disk has to migrate with the planet because the gap has to move with the planet. And then the physical process becomes different. That's why the migration becomes proportional to the disk viscosity, because the disk viscosity tells you on which time scale the disk can rearrange itself and the gap can move. But also the planet becomes so massive that its mass becomes typically comparable with the mass of the surrounding disk. And then you enter into inertial problems, right? If you are a small guy and you try to push a Japanese sumo, you will not push him very far. And if you push a little guy, you can push him much more violently. This is just an issue of inertia. Once the planets become hundreds of Earth masses, the inertia can become significant, in particular once the disk starts to lose its mass. So we really have a braking regime if, well, I cannot plot anything, but if you have here the mass growing, okay, first for small masses, migration is like this. Migration speeds increase with the planet mass, but then if the planets become massive enough, migration is like this. So it decreases with planet mass. And that's why, for instance, Saturn, which is lighter than Jupiter, tends to migrate faster than Jupiter, approaches Jupiter in resonance, and once they are in resonance, their migration stops because of their common effect with the disk.
Thank you. And another question. So the population of hot Jupiters we see today, so they can be they can't be then due to this disk migration, because and why the for the small planets like the super Earths, smaller planets, they stops near the inner edge, but for the giant planets, what ultimately makes them stop?
Yes, so the origin of the hot Jupiters is ambiguous. At the beginning, it was thought, well, it's migration. But then people realized that there is something odd with this idea. Hot Jupiters are typically alone. There is nothing behind. And despite they are circular, because they are tidally circularized, if they were eccentric, they would have been circularized. They are often very inclined relative to the stellar equator. So, and if a planet migrates in the disk, if the disk is equatorial relative to the star, it should remain equatorial in the end. Now, of course, we can imagine that the star flips relative to the disk and the disk is not equatorial. But all of this prompted another idea for the origin of super or hot Jupiters, which I think has a lot of merit and tend to be my favorite one. As you can see in this diagram, so this is the tidal circularization curve, or any planet above this curve would be tidally circularized following a line parallel to this. Okay. So the eccentricities of giant planets are large, and giant planets eccentricity reach this kind of curve. So it's unlikely that giant planets ended their eccentricity excitation, limited their eccentricity excitation just below this curve. It's likely that when the giant planet instabilities occur, some planets acquire eccentricity of 0.4, 0.5, 0.6, 0.9, sometimes even higher. And when this happens, tidal circularization kicks in, and the planet follows this trajectory by tidal damping. Tidal damping damps the eccentricity, but also reduces the sign major axis. And where does this line drops? In the hot Jupiter region. Okay. So hot Jupiters could have reached their location, not only by migration, but by extreme eccentricity excitation and tidal damping. And this process has some merit because extreme eccentricity excitation comes together with extreme inclination excitation. And whereas the tide damps the eccentricity, does not damp the inclination. So this could explain why these hot Jupiters can have very large inclinations relative to the equatorial plane of the star. It explains also why each hot Jupiter is lonely, because if the hot Jupiter that we see now was in the past a giant planet with 90% eccentricity, clearly there is nothing else left in the system. Okay. And also explains this gap that I discussed at the beginning between hot Jupiters and warm Jupiters. If everything migrated in, you would expect a continuum. These are the planets that migrated the fastest or started to migrate first, and so they could go until the edge of the disk. These should planets that migrate a little bit less, and this a little bit less, and this even less. So why should we have a bimodal distribution with a gap in the middle? If instead migration typically is relatively slow because the disks have low viscosity, typically bring giant planets in the warm Jupiter regions. These are outliers, planets that had exceptionally long migrations, and these come in a different process through eccentricity excitation and tidal circularization. So I think that hot Jupiters, which by the way are just a minority. Here you see a lot of points because they're easy to find, but there is 1/10 of hot Jupiters compared to warm Jupiters. I think that hot Jupiters rather come through eccentricity excitation and tidal damping rather than migration. I don't know, Saurav, what would you think?
I totally agree with you.
Okay, then we must be right. We have to.
Okay, I think that's a very good note to end this discussion. We are right.
Okay, it's a nice way to end. Yes.
Thank you, Morbi.
You're welcome.
Clap on behalf of everyone.
Thank you very much. Hope you enjoyed, and if there are other questions, you can always send them to me by email. Saurav has my email, so you can give it around. It's on my webpage too.
Thanks. Bye.
Okay. Bye-bye. Thanks a lot, everybody. Bye-bye.